Today there's very little theory, extremely little. However, the problems that will come after this will be the hardest you've gone so far. So let's make sure that the little theory that we do today is very well understood. Now we will start with Newton's second law. And Newton's second law is basically the definition of force. What Newton said is, well, force is something that causes an acceleration. That's very good. That's all well and good. So here I have my body, and a force is something that will cause it to accelerate. But that's not good enough for a definition. And the reason for that is that this is physics. This is not biology. It's not enough to just state something qualitatively and then go to sleep. We need a statement that gives us not only what something does, but that enables us to calculate it. And that's what Newton's second law says. Newton says, well, force is something that causes acceleration, and this much acceleration on this much mass is this much force. So if you know the mass and the acceleration, you can calculate the force. That's what it does. Now, Newton's first law, which you should know, second law, which you should know already from the IGCSE, says that the force equals the mass times the acceleration. You will notice a little difference from the IGCSE, which is that now I'm drawing little arrows on these things. And the reasons for this is that both the force and the acceleration are vectors, which means that the force has a magnitude, but it also has a direction. And this is telling me that however, wherever the force is pointing, that's where my acceleration is going to point. So what this is telling me really is that force is proportional to the acceleration, and the mass is the constant of proportionality. The more mass something has, the harder it is to accelerate it, the more force I need to do to achieve the same acceleration. So this is something that's almost common sense, but bear in mind that when Newton came up with this thing, this wasn't common sense at all. Most people thought that forces made things move, not accelerate. Most people associated lack of force with things being still, not with things moving at a constant speed. And also, Newton's stroke of genius was to find a quantitative way of referring to force and to use mass as the constant of proportionality. So again, this may seem obvious to you, but it certainly was not at the time. Now, the good news about this equation is that it not only defines the force, but it also defines the units of force. And we did this the other day, but I'm going to write it down again because I know people don't have great memories in general. So the units of force, as we said, are the newtons. And we can derive these units by taking a look at the equation. So these are newtons. These units here combined have to be newtons. Now, what are the units of mass? Well, the units of mass are kilograms. So, and what are the units of acceleration? The meters times second to the minus 2. So 1 Newton is a kilogram times second to the minus 2. Now here, I'm sorry, but I used this wrong. This should not be here. So this should not be here. This should be like this. Units of force equal newtons, which equal kilograms, meters times second to the minus 2. If you saw this, well done. If you didn't, you need to be more precise. So I am leaving it here in this video so that you realize that it's very important that when some notation means something, we need to stick with it, and we can just make things mean whatever we please. Now, how are we going to use this second law? Well, very simple. Every time that we have a body, like this, we will see there's a bunch of forces acting on it. And what we're going to have to do is to add them up. And then, once we've added them up, if we know the mass, then we will know the acceleration. However, we have a little problem, right? Because you've never done this in 2D. You've always had something like, oh, here's my body, here's my two forces, what's the total force? And now suddenly you have things that are all over the place. So how do we do this? Well, the way we do this is by parts, one thing at a time. These things point in one of two directions, either vertically or horizontally. So what we need to do is to split this problem in two. We need to split this problem into its horizontal components and into, vertical components, and then into its horizontal components. How do we do this? Well, using our old friend trigonometry. If you're not good at trigonometry, you are going to have lots of problems in physics. So you'd better, study. If you need some help, I will be happy to help you in class. So anyway, what we'll do is Well, if I know this angle, so let's just say theta 1, and let's just call this one theta 2, and let's just call this one theta 3, then I can figure out the components of these forces. So I can say, okay, well, the horizontal component of this force is this here, and I can calculate this with the cosine. And then the horizontal component of this force here is this one here, and I can calculate this with the sine of this angle. Yeah, and then the horizontal component of this one is this one, and I can calculate this with the cosine. And then once I have all the horizontal components, I add them up, bearing in mind that this one will be negative, this one will be positive, and I will have a total force in the x direction. And that will give me the acceleration in the x direction. But I will not be done yet, because there's still a vertical problem to be solved. So then I will have to work out the vertical component of this force that I will get. So in this case, I will get it with the sine. And the vertical component of this force that I will also get with the sine. And the vertical component of this force that I will get, in this case, with a cosine. Now, if you don't know why I'm using cosine at some point and sine at some others, then you need to refresh your trigonometry. But the basic idea is that every time that I want the side that's next to the angle, then I'm using the cosine. Every time that I want the side that's away from the angle, then I'm using the sine. The way that I remember this is that if this is an angle, the cosine is the horizontal projection. So imagine that here's the sun, and this makes a shadow here. So the cosine is the shadow, and then the sine would be the shadow on the wall. So sine would be this thing, shadow on the wall, cosine is the shadow on the ground. Before we move on to Newton's third law, we're going to talk about terminal velocity for a second. And you've done this already, so this should be absolutely no problem because you've done this in the IGCSE. So imagine, for example, that this is the ground and this is a plane, and I jump off the plane. Okay? Now, what the law of gravity tells me is that I'm going to be accelerating downwards so that my speed is going to get higher, higher, and higher, and higher. However, that's only if there was no air, but there's air. And as I told you, the resistance of the air gets higher and higher and higher as the velocity gets higher. Just because it's like walking through very, very strong wind. It gets higher, it gets harder the stronger that the wind is. So as I move faster through the air, it's as if there was some really strong wind hitting me, right? Okay, so what happens is that there's this force of gravity, and then there's this force of air resistance, but this force gets bigger as I fall because my velocity gets higher, and therefore this force gets bigger and bigger and bigger. Now, of course, there will be a moment when this force is exactly equal to gravity, and then I won't accelerate anymore, and my velocity will stay the same. So this can't get any bigger. So once this happens, my weight and the air resistance will balance, and then my velocity will stay the same. This velocity is the terminal velocity. We call it terminal velocity because it's the one at the end. It's the one that I will have when I hit the ground. And it just never changes anymore. So, terminal velocity. If we plot this, we will have something like this. So here's my velocity, here's the time. At the beginning, my velocity is increasing a lot, but then as it gets bigger and bigger and bigger, it starts to reach a point where it's always the same, and that's because the air resistance is exactly the same as the weight. Okay, now we're finally ready for Newton's third law, and people always struggle with this, and they struggle with this because I guess it goes against their common sense, and I think basically because they don't understand what it's applying to. And what Newton's third law says, if I have two bodies, A and B, and body A does a force to B, so force of A to B, then body B is going to do exactly the same force to A, but with an opposite sign, so in the opposite direction, force of B to A. So it's very important that you understand that this law refers to two different bodies. The two forces are not done to the same body, because if they were done to the same body, then nothing would ever move, because these two forces would be the same, this would be still. But that's not the case. This does a force to this body and send it in this direction, and then this will do a force to the other body, which will go in this direction. So the two forces apply to different bodies. the force that A does to B will be done to A in the opposite direction. So how does this work? So same thing as always. Imagine that I'm here and gravity is pulling me with a certain weight. Now, a lot of people think that the reaction force to this is the normal. So gravity is pulling me down, and because of this, there's a normal force against me. But that's not true. The reaction force to gravity pulling me is me pulling the earth. So I can imagine it like this. I could not be in the ground. I could be, I could be here, falling from some height. I would still have a weight. So the force that the earth does to me, that's the weight, I will do to the earth, which means that I'm also pulling the earth with the same force that the earth is pulling me. So the question is like, well, but I'm moving, but the earth's not moving. So how is that possible? Well, that's possible because I'm tiny and the earth is huge. So the force that moves me a lot barely moves the earth. I mean, I do a force of my weight to the earth, and the earth barely feels a thing. Okay? So then why does the normal happen if it's not a reaction force? Well, the normal is a reaction force, but it's not a reaction to the weight. It's a reaction to the force that I am doing on the ground. So the weight is pulling me down, so that's the weight. And because the weight is pulling me down, I am going down, and then my feet are doing a force on the ground. And then the ground is doing a force on my feet in exchange. So the normal force is not a response to weight, it's a response to how much I'm pushing the ground. And that's why if I jump, I go up. So if I jump, I'm pushing this harder than my weight, and then I go up. Because I can push the ground harder than my weight. Because it's the force that my feet do to the ground. So this is very important. You need to understand this very well. And this thing about gravity and the earth is a classic example of where people get things wrong. They will ask you in the exam, typical multiple choice question, the earth is pulling a person down, what's the reaction force? And people will say the normal force. Well, it's not. It's not. The reaction force is the force that I'm doing to the earth up. Alright, so that's all, folks. Now, after this, you should be able to draw forces in a body, which you hopefully were able to do even before, and then apply Newton's second law in order to calculate the total force and then use that for the acceleration. Then remember that the acceleration and the force have the same direction, and you also know that. And finally, you should be able to identify the action-reaction pairs, which means that if I'm acting on a body, I need to know that if I'm acting on this body is acting on me, and that these pairs happen in different bodies, not in the same place. Remember, this is the action, this is the reaction. Alright, so good luck. There's some really hard problems coming up. I'll be there to help.